The Future in Biophysics Symposium looks to where new tools are changing what we can actually see and understand in biology. Keith Cassidy studies massive, flexible biological particles that have resisted structural biology for decades, including LDL, the particle closely tied to heart disease, by combining experiments and AI-based modeling to reveal how they are built. This sounds fascinating. Thank you for joining us.
Thank you.
I want to start off with, I believe LDL is one of the most important particles in biology, right? But it's also seen as structurally difficult to pin down. Why is that?
Yeah, you're absolutely right. So LDL is massively important for cardiovascular disease. It's kind of been at the center of research for 5 decades or more. And, it's one of those rare molecules that have kind of entered the public consciousness. Most people know it as bad cholesterol, even if they don't know what it actually is. The kicker is that we haven't known what this thing looks like structurally at high resolution, despite it being so medically relevant. And so this is because it's really big, it's really dynamic, it's filled with disordered lipids, and this is kind of a perfect storm of challenges for structural biology. It's also really heterogeneous, both compositionally and conformationally. And so, the working components have to do a lot of gymnastics in order to kind of carry out the function of LDL. And so again, it's just a really difficult structural biology question.
So on that, you were looking at 3 very specific methods to study these proteins, and it's very interesting because you had to look at all of them together to find something that couldn't be revealed individually. Has this never been known before?
Yeah. So it's kind of a theme, in biophysics these days. Things are really interdisciplinary, and so the techniques we used were cryo-electron microscopy, AI or artificial intelligence, based structure prediction, and then molecular dynamic simulations. And so I just want to shout out my colleague back at Mizzou who did all the beautiful Cryo-EM for LDL, and these other lipoproteins we're studying. But basically, these can kind of come together and give us a self-consistent, physically realistic model of our protein system, and then simulations can kind of take that even further in order to tell us more about the lipid cargo and things that then we can use to design new experiments, and hopefully, through this process, really understand much better about the role that this is playing in cardiovascular disease.
And how does this translate to the people we care about, cardiovascular disease, those affected by it? I know that you have a reason for being in this industry as well, and that kind of ignited your passion.
Yeah, indeed. So heart disease is something my family struggles with, and so there's a kind of a deep personal relevance there. Really, cardiovascular disease is massively complicated. But just to focus on some of the key questions that we can now ask, by seeing the shape of ApoB and kind of how it interacts with the lipids, we can begin to understand how it's kind of undergoing these dramatic changes in conformation as the lipid cargo changes, and we can also begin to think more concretely about how the LDL receptor binds to these LDL particles. And so that's what's necessary for clearing this from the bloodstream. And so when that's working well, plaque doesn't build up. But when we know that there's an important size dependent on these LDL particles, so not all of them are equally dangerous. And, with these new structures, we can maybe see some signatures that we can use to kind of help target the really bad ones.
What drew you to working in this realm, in this field? Is it something that is impacting society that really needs a solution, or it seems to be rather complex? How come you haven't steered away from it and many others have?
Sure, as you point out, cardiovascular disease, number one killer. These kind of LDL associated variations are one of the big driving forces. There's a huge societal impact from figuring out how these proteins are working. I think also the timing is right, so between the Cryo-EM community and the MD community, decades of work have gone into building up the tools that are necessary for tackling these challenging systems. And now that we have AI coming in and kind of launching us into this new realm of structural biology, really there's an opportunity that wasn't here just a few years ago. And so that was something Zach and I noticed, and so that's why we kind of just took it by the horn, so to speak, right?
Well, it sounds like the future is bright in this industry and having more answers come our way over time.
Yeah, it's a really exciting area. I think a lot of important future biophysics is going to happen here.
All right, so we have to keep us updated. Thank you so much for being here.
Thank you.